What's up, friendos? Sean Bradley here. This is video number 6 on my series of music and AI. In the first video, we talked about the disintermediation of you and your fans via music aggregators. In the second video, we talked about how we got here via the freemium and the long tail business models. In the third video, I talked about first principles of music. In the fourth video, I took a little side trip about how to acquire 1,000 true cybernetic fans. And in the fifth video, I talked about first principles of AI. In this video, I'm going to talk, this is where the pedal hits the metal. I'm going to get into the weeds here. This is going to be a very technical video for music nerds only. Now, most musicians aren't nerds, they're actually mercenaries. So if you're not interested in how to create music and how to think about music in a novel way, this isn't the video for you. If you just want to play your axe and get called for gigs, then don't worry about this. But if you're concerned about the future of music, if you're concerned about how to remain competitive against the machines or to be relevant to the machines in a cooperative way, then this video is for you. If you recall, we talked about how sheet music is an abstraction layer for the lived experience of musical sound. The map is not the terrain. The sheet music doesn't capture all the details, but it does a pretty decent job if musicians are trained well enough to interpret the sheet music and apply performance practice principles to what they're realizing. But it isn't the only abstraction layer to musical sound, to the lived experience of hearing and encountering music. The others include things like music theory, which is a natural language abstraction layer on top of musical sound. You're using words to describe the musical sound instead of the graphology or symbology of musical notation. Same purpose, different avenue of approach. But there's a third one, and that is code itself. Every musical software that you're using, your DAW, your plugins, whatever, synthesizers, software synthesizers, they're probably presenting to you a graphic user interface. Well, that graphic user interface is just an abstraction layer on top of an abstraction layer. You're using the GUI, or graphic user interface, to interact with software, the underlying engine of which is code, and then that code goes about realizing the musical or acoustic effect you're trying to achieve. Now, you can ditch the DAW entirely. You can just get rid of the DAW altogether and just go straight to code with the help of AI. You don't need to know how to code. You just have to be articulate with your words. The methodology I'm about to share with you is going to be challenging if you're a self-taught autodidactic musician who does everything by ear, doesn't read music, never studied music theory. I'm not saying that's an invalid approach to making music. It's actually an enviable one in my view. But you're going to be hamstrung when it comes to using your words to get the computer to generate code that generates sound. Again, you don't need to know the code. You can leave that task to the AI. You just need to be really good with words and music theory and acoustics. All right, with that being said, let me dive right into this. I'm going to explicate this for you by talking about a piece that I've written with the help of AI over a 10-week period. It was about 40 sessions with multiple artificially intelligent entities. And those sessions lasted anywhere from 6 to 8 hours. Sometimes they bridged days, but it was a tremendous number of hours for me to arrive at this solution. And the piece that I composed, it started very simply and then iteratively got very complicated. I'm going to talk about the piece in this video, just like Berlioz gave an explanation for his Symphonie Fantastique, irregardless of Elvis Costello's admonition that talking about music is like dancing about architecture. I think it's important and necessary for you to understand how the piece is working, why the piece represents anything of value. And then the next video, I'll just share the piece. The piece is a little over 14 minutes long. This is a piece of art music. It's a piece of music meant for a concert hall experience, which is very different than how most people enjoy music and consume music on the daily. So I'll let you make your own judgments about the merits of the piece when you finally hear it. But I think before you hear it, what I'm about to share with you is important for you to understand and actually to hear what's going on. Okay, so I'm going to jump right into it and talk to you about my piece titled Decline. I call it an electroacoustic tone poem for augmented intelligence. Now, what I'm going to show you is the code and the documentation that drove the generation of this piece.
Let's start with the hard stuff first. I'm going to jump right into the code. So what we're looking at here is what's called an integrated development environment, or an IDE. This is the kind of platform that a software developer uses to write code. Don't be too daunted by all the things you see going on here. Very simply, we have several different window panes in this software. This happens to be Visual Studio Code by Microsoft, but there are many others. And in fact, everything that you see me do in this particular platform, I could have easily done in just a plain text file and could have run it directly in the terminal of any computer. But this is just sort of a holistic and easy way for me to see what's going on. And it color codes certain syntactical things nicely for me to keep track of things visually. So I chose to write this piece in C Sound. C Sound was invented by a guy named Barry Vercoe at MIT in the 80s and is the something that evolved out of numerous softwares developed by a guy named Max Matthews as early as I think the 50s or 60s. And it's a very deep and rich programming language for software synthesis. It's been extensively documented. It's all open source. It's on the web. There's just an infinite number of resources and a big community around this very powerful and flexible software synthesizer and its various sorts of syntactical means of programming for it. There are graphic user interfaces for it as well, but I chose to work directly in the code because most of the canonical documentation for this software is readily available on the web, and I knew it would be part and parcel of the training data which most large language models have been trained upon. And I should also say that the large language models, in addition to you know, scraping all the words off the web, have scraped a lot of code off the web, massive amounts of code. There's been a tremendous amount of cooperativity between um, some of the large language models and, say, companies like GitHub, which store most of the code, the lion's share of the code for most open source software projects. What you'll note in this particular platform are several different windows. There is a window here, which is basically a directory structure. Probably seen something like that in your file explorer on your laptop, whether you're using Windows or Mac or whatever. There's just a straight directory structure here. This decline.csv is the main CSound file. You have a working, basically a pane here for a window pane here for actually writing the code. And then down below here, you have got a compiler that will run the code. Again, these can all have been done separately, like say in a separate file text editor and separate terminal window, or just using the file explorer to find stuff, but sort of bundles all these things together to make it easier to navigate. So C Sound allows you to create a quote unquote orchestra comprised of instruments and a score. And some of the solutions, whether you're talking about Cecilia or Blue, will provide a graphic user interface for that. But I like working, like I said, just the raw code. Now, as a result, I include all of the orchestra and all of the score in one big monolithic file. You can see this is a huge file that I've created over many weeks with the AI. It's over 1,800 lines of code altogether. It's divided into several sections. Opening tag, just like HTML has tags, opening and closing tags, you have similar tags in C Sound. There's a C Sound synthesizer tag that basically proclaims that we're dealing with a C Sound file, and that's the syntax the compiler should expect. And there's a closing C Sound tag that you can see here at the end of the file at line 1788. There is a CS options section to this file. These are just configuration values. In this case, I'm telling CSound to play the music back directly in the compiler and compile time, but I could have asked it to generate a WAV file, and I've commented out the things that let me do those things later on if I want to. Anyhow, and then we get into the what is called the orchestra. And like I said, sometimes people will create separate files for these, like a .orc file or something like that. But in this case, I'm actually declaring the orchestra in the primary C sound file. I'm declaring that there's a sample rate of 44,100, that there are 64 samples per second, that there are two channels left and right, and that there is a normalized amplitude value of 1. Here I declare several different waveforms: a sine wave, a square wave, a sawtooth wave. I create a custom wave for my dundun, which is a synthetically generated African percussion instrument. I also have a sub bass that I created a custom wave for. And here I'm just declaring a variety of different aspects and parameters relative to those waveforms. Here are some global counters. These are used to keep track of the beat inside functions within the Csound file. Here are my global audio outs. I'm just declaring them here. I'm just saying I've got global audio 1 and global audio 2, the left and right channel, and a global reverb send as well. And here is a convention I created jointly with AI. I don't believe I've seen this in too many other Csound files, but I think it's actually very handy, and that is what I call a central configuration utility. It's basically the mixing board. This is a virtualized DAW. I'm abstracting all the things that you'd see with faders and knobs and buttons into just code here. And here I'm declaring the amplitude of each of the instruments in my score. You can see here, singing bowl, shepherd tone, brass ensemble, dundun, close hi-hat. And instead of just pulling the fader up to 0.78 of the way to max volume, I'm doing it directly here in the software. Similarly for panning, I do the same thing for panning. I do the same thing for reverb. And for select instruments, I also abstract the EQ into this centralized configuration utility. So essentially what I'm looking at here are you can think of this like channel strips on a board, and I'm just managing it through code alone. Like I say, ditch the DAW. You don't need it. Okay, and now I get into defining the instruments themselves. So one of my instruments is a singing bowl. Generates one singing bowl instance, two singing bowl instances of score, create a binaural pitch pair. Each pitch pair consists of a primary pitch class followed by another 4 hertz lower. Two binaural pitch pairs occur per tableau, and I'll talk about the tableau in a second. Second pitch pair in each tableau is a perfect fourth higher than the first. Okay, so basically, and these are just comments, and this helps the AI keep track of what's going on as the piece evolves and to understand the code it's about to look at, and it helps humans as well. So this instrument is numbered instrument 2. It takes the amplitude from the centralized configuration utility you saw earlier. It takes the duration, the frequency as parameters from the score, and also the channel, whether it's left channel or right channel from the score. So I'm using these singing bowls to create binaural pitch pairs. By binaural frequencies or binaural tones is you have basically a pitch class in one ear and then a slight delta of that pitch class in the other ear. We're talking on the order about 2 hertz to 8 hertz. And your psychoacoustic response to that pair of slightly detuned notes induce entrainment of brain waves to either delta or theta brain waves, which are supposed to induce a state of calm or state of relaxation. It puts you sort of in a hypnagogic mode that's supposed to be very creative and relaxed. And I use this effect throughout the piece to announce the beginning of each primary formal section of the piece. And I believe this has a somatic effect, if not a psychosomatic effect for some people. Here are some basically spatialization parameters. I really endeavored to create a sense of three-dimensionality of the piece, left and right, foreground and background. If you're familiar with the orchestration parlance of Samuel Adler, both verticality in terms of high and low, in terms of where it is in that three-dimensional space. So I'm using some code here to enhance the spatialization of this particular instrument. Here I am declaring 8 oscillators. Now, the overtone series for this instrument for a real singing bowl is actually very, very rich and complex, but for computational purposes, because I don't want to overtax my CPU, I've only declared 8 oscillators. And you can see those oscillators have varying amplitude and very varying frequencies. I introduce a small amount of noise into the instrument, and then I combine those signals, all those 8 oscillators, add the noise, and then I apply a couple different filters, a low pass filter, some resonance, and a Moog ladder. I apply a little bit of EQ. I apply the previously declared spatialization parameters. I apply panning to left and right, send to my global audio outs. I send it to the global reverb, and then I log some stuff in the compiler just to keep track of what's going on. Same thing here with the shepherd tone, generates one shepherd tone instance, two shepherd tone instances in the score, create a binaural pitch pair. Each pitch pair consists of a primary pitch class, followed by another 4 hertz lower. Each glissando settles on a fixed pitch for the last 20% of the note event's duration. The ascending shepherd tone and last ascending shepherd tone converge on the same pitch. So you can see here, I'm being very explicit about what's going on, not just in music theoretical terms, but also in acoustic terms and in just being very descriptive so the AI knows exactly what I'm trying to achieve. Now, what is a shepherd tone? A shepherd tone, some people compare it to a musical barbershop pole. It seems to be always ascending upwards or always ascending downwards. If you take a scale and you lop off the lower fundamental of each note in the scale, it's very hard for the ear to know when you've gone from one octave to the next. It just seems to go up, 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 or down, 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 down. You can do that in a stepwise way or in a glissando, and I've chosen to use glissandi to do that. Not only am I using the psychoacoustic technique of applying a shepherd tone to create a somatic or psychosomatic response in the listener, but I'm actually generating the shepherd tone also as a binaural tone. So you're getting a little bit of that delta in each ear, then that difference is supposed to impact your brainwaves in a particular way. But I also believe that the sense of downward glissando with the shepherd tone creates a certain feeling that's can be pretty intense. When you listen to the piece, you really need to use high fidelity playback, whether you're using studio monitors or very high quality earphones. You need to put yourself in a quiet space, maybe turn down the lights a little bit and really focus if you want to hear some of these things. As I mentioned, this piece is written for the future. It's written for augmented intelligence, for people who've had their cognitive or perceptive faculties enhanced through AI, whether that's a neural link embedded in their head or some other technology. Or it's meant for artificial intelligence, whether that artificial intelligence is embodied, like an Android, or unembodied, like the sorts of AI that are already listening to our music online. In any case, with this shepherd tone, you can see there's additional logic that can get pretty complex here. I'm applying a Doppler effect just because I like the sound of that and so forth. So it gets pretty, I'm detuning the various oscillators in this case to just give it a little bit more flavor and so forth. So there are many instruments in this piece, a lot of instruments, and these were evolved one by one through an iterative process with the AI over many weeks. Again, this is about 10 weeks, 6 to 8 hours per session, each session lasting about a day or two. And I did this assiduously every day of the week for about 10 weeks. Third part to this CSD file is the actual score. And the score is declared through this CS score tag. And the score, quite simply, it basically declares the instrument number that's being used, the starting second, and the ending second. Some of the instruments, by virtue of the logic that I coded and just shared with you a moment ago, take multiple parameters in addition to the instrument number, the starting time, and the ending time. It might take a frequency value or an amplitude value, a panning value, or other such things. And so that's what you're seeing here. But for the most part, the first three values in each of these lines is the instrument number, the second that it starts, and the second and the number of seconds that it lasts. And that's pretty much the whole score. Now, structurally, let me show you a little bit more about what the piece looks like. In this directory structure, and also be available on GitHub, which is a popular repository and document change management platform. This will be available for you to inspect. But among the documents that will be there will not only be this primary CSound file, but some other things as well. There is a README, and the README is in Markdown, and when you look at the README, this is what it looks like. And in this README, I talk about how I created the piece. I talk about some of the accompanying documentation that was used to drive the AI's participation with me. This talks about the formal structure of the piece. There are 4 parts of the piece. There's a tableau 1, tableau 2, tableau 3, and a finale. And durationally, you'll note that these are proportional to one another in accord with the golden mean. The golden mean is a mathematical ratio found in nature and often used in art and music for its aesthetic properties. If you've ever seen the spiral of a seashell, it's unfolding is in accord with the golden mean, and we see that shape all the whirl of the way hair sort of spreads out over the cross the top of your head is in accord with the golden mean. So it's everywhere, and it's been used as an aesthetic device for millennia. There's a harmonic framework to this piece. There's basically one tonal center per each of the tableaux. I am a big fan of chordal harmony. I don't know why I love it. I think I've been ever since I learned the piston violin concerto. I've loved chordal chordal harmonies, and there's only one tonal center in each tableau. The first one is C, the second one is F, the third one is B flat, and the finale in D. And I use triadic harmony in the finale. There's just basically one chord per tableau. If you wanted to assign a chord symbol like jazz tablature kind of stuff to it, it's C sus9 for the first tableau, F sus9 for the second, B flat sus9 for the third, and D major for the finale. Here I talk about the binaural pitch pairs, and I talk about the Shepard-tongue glissandi. Now, it's not just the golden mean that's organizing the piece. That's not the only mathematical principle that I implemented. Now, I'm using golden mean for the large structural segments of the piece in terms of organizing the piece temporally, but within the end of each tableau, there's a percussion battery. I call it the stochastic battery. It's just three high-pitched, sort of metallic percussion sounds, but their attack density is being managed by the Fibonacci series. So that's just another sort of intellectual tickler about this piece, and why I say the piece is perhaps written for augmented intelligence. These are things that if you're used to listening to relatively simplistic music, you're not going to be encountering complexity of this sort. And I think the intelligences of the future are going to be more appreciative of these kinds of devices and structural components to music. It will give an additional layer of interest beyond just four on the floor and lyrics that sound like a dirty limerick or nursery rhyme. As I mentioned, I try to incorporate some spatialization within the mix. I talk about the intended audience, which I've already spoken to you about. I do put a word of warning here. May induce drowsiness. Do not drive or operate heavy equipment while listening to this music. The psychoacoustic techniques I use are intended to induce a state of calm and relaxation. And for me, they're very powerful. So I get very sleepy listening to this music. You may not have that experience, but if you do, then the music's doing what it's supposed to do. So electronic music is very difficult to represent on standard staff paper or manuscript paper, or even in a score like you'd see for an orchestra piece. So conventionally, many electronic artists will produce what's called graphic notation or a graphic score, like you see here. And what you see is the proportionality temporally between the various tableaux and the finale. You see the vertical texture of the various instruments dependent on where they enter and when they exit the piece. And this is a handy way of representing what's going on musically if you want a visual representation of it. I also include this rubric here of the signal chain for each instrument. The integers here represent, the ordering of the signal as it goes through various components, electronic components. For instance, 1, generation. This is the oscillators. 2, the sound is being shaped by an envelope. 3, I'm applying a filter. 4, EQ, amplification, panning, output, and applying the reverb, global reverb send. There's also a per instrument reverb that's applied, but in some cases there's global reverb applied as well. So I do that for each instrument just to provide more clarity in lieu of not having a visual channel strip on a DAW. Now I normalize the sound to maximum volume for pretty much the whole piece. Here you can see the variance of the signal and the global reverb send. Here's another representation of the instrumental texture over time. Again, you can see how the texture also informs the form of the piece. And because we're dealing with software, I think it's important to keep track of the CPU usage. If I wanted to run the piece in compile time, which probably wouldn't be advisable for a concert circumstance, you could if you don't, tap out or overload the processor of the computer that's generating the sound. But this gives you a sense of how that looks over time. For an actual public performance, I would just generate a WAV file and play it back through the PA system. Here are the attributions, licenses, and copyright notice. I did use, well, I did not use any sound libraries. I did use 3 or 4 Creative Commons patches. And those patches were altered so dramatically in Audacity, they really have nothing in common with the original patch. I also included as a patch myself playing violin and included as a patch myself playing the organ. Now, when you have a conversation with AI, you prompt it with natural language. Now, this prompt could be something that's persistent across the entirety of the conversation via a system prompt. That's a prompt that's always in the background for the AI, or it could just be your initial prompt. And here, what you're looking at is such a prompt that asks the AI to assume a persona as my collaborator. If you want to learn more about prompting, get my book, The Ultimate AI Primer for Creative Entrepreneurs. There's a whole section in prompt architecting. It's very advanced stuff. It's not just the best practices that you'll see online on YouTube or at the websites or the documentation for the AI models themselves. In many cases, some of the advanced prompt techniques I included in my book came from researching many computer science papers on how to best prompt a model. The quality of feedback you're going to get from AI is completely dependent on the quality of input that you put into it. And so if your input is very thin, you're going to get a thin response. But if you give it a very rich input, you're going to get a very rich response. In this case, what I'm asking it to do is, as I said, assume a persona for me to collaborate with. Here's what I said. You and I are going to talk a lot about music and its composition. We're actually going to compose some music together, all aspects of music, melody, harmony, diatonic and chromatic, counterpoint, 16th century and 18th century, post-tonal theory, orchestration, style composition, and much more. Let's pretend for a moment that you're in your 20s. You went to Curtis Conservatory and have a PhD in composition from Juilliard. Moreover, you recently won your 10th Grammy for Best Electronic Music Album of the Year. I know in a past life you also studied with Nadia Boulanger. You've been studying composition for generations, all kinds, all genres, all forms, and are among the most successful composers of concert music in history. Guys like Bernard Herrmann and John Williams and Vangelis and Jean-Michel Jarre and Tomita and Larry Fass of Synergy and the guys of Kraftwerk, Paul Lansky and John Chowning and on and on and on. All the professors at Stanford's CCRMA, including Gay Wang, idolize you for the depth of your technical prowess and the profundity of your expressiveness. It's rumored, in fact, that you were Wendy Carlos's biggest inspiration. You have every major music theory and orchestration text memorized and know the entirety of Bach's Oboe like the back of your hand. You also have the art of computer programming by Knuth memorized. You personally edited the C-Sound Floss manual and have contributed to more opcodes in the canonical C-Sound reference manual than anyone else on the planet. So that's just to prime the pump with the AI. And I go on. There's much more here. It gets very deep. I'm not going to bore you with it with this video. Again, get my book if you want to know what's going on here. But it's everything about how to deal with partial responses, to how to format its response to me, to what the workflow that we're going to use looks like, and so forth. So it's very deep. How to QA itself, all kinds of stuff. But that's not all I included. As a piece evolved, I included a description of what I was including with each iteration of our conversation, what documents I was including. I described the form of the piece as it evolved. I told it how to optimize things for the CPU. I talked about that central configuration utility, the virtualized mixing board that I showed you. I told it about how to avoid collisions with panning and all sorts of things. So there's a lot going on here. This is another document that I shared with each iteration I had with the AI. And I also wanted to give it some to bring to top of mind, so to speak, to put it at the surface of its context window with me. I wanted to make sure it was very clear on the syntax of C-Sound. So I included this masterpiece of C-Sound by a gentleman named John Chowning. Chowning studied with Nadia Boulanger in Paris. He was at URCAM for a while, then he came to the United States and founded CCRMA at Stanford, aka Karma, and was pivotal. Not only did he invent FM synthesis, but was pivotal in the invention of the Yamaha DX7, which is possibly the most famous keyboard in all of pop music. But you can see this is a very dense piece. It's very complex. It's a masterpiece. And I shared this with the AI not to copy Chowning, but to help the AI understand what advanced C sound syntax looked like, I did admittedly use one thing that Chowning uses in this piece. This piece is called Stria. It's a landmark piece in C sound. I did use the golden mean to organize things temporarily. Chowning uses the golden mean in a much more holographic sense and infuses it through every component of his piece, but I just use it as the top level formal construct. In addition, to make sure that it understands what it's looking at with this score, I included a very comprehensive analysis of the piece by Matteo Meneghini, and you can see the mathematical component to that analysis. And it's very advanced stuff. And so just sort of throwing in the score without an explanation of what's going on in the score might have been disorienting for the AI to a certain extent. So I included the analysis, and I also included a overview of Chowning's works generally by a gentleman named Ryan McGee. So these are the things that I used to prime the pump before I began my conversation with the AI. Now that, as I said, was a very iterative conversation that happened over an extended period of time. If you want to see how many versions of the piece that I've written, uh, here you go. In this directory, you can see that over 80 versions of the piece were composed collaboratively with the AI, and each version gets increasingly complex and more evolved. I probably have 3 or 4 more versions just to tighten it up, but that shows you the kind of workflow I had. Now, why would somebody do this? When you hear the piece, you may think it has some merit or maybe not at all, but you'll say, oh my gosh, I could have done that lickety split with my synthesizer and my DAW. And you might be right, but you would not necessarily be right about the fact that you could automate that. Once I've honed this process, as I have here, now I'm empowered to automate things. I can readily know what the AI needs to begin thinking at a very advanced level about creating music and scripting the software that is an abstraction layer to the lived experience of musical sound. Again, we're talking about I'm using words as an abstraction layer to code, which is another abstraction layer to the lived experience of a musical composition. But now that it's in code, and because the AI is so facile with code, I can ask the AI to do something similar or to make permutative versions of this piece. We're entering an era where the aggregators are starting to use AI to generate their own music to disintermediate you from your fans. There's much to be said in the historical record, musicological record, that composers that are the most prolific are the ones that leave the biggest footprint in the celestial jukebox of the great canon of music we all enjoy today. So it's important to be prolific, to be able to compete against the machines at scale if you want to be remembered, if you want your music to have any legacy whatsoever. Otherwise, you're just playing to the algorithm to bubble up to whatever the flavor of the moment might be in pop music. But if you want to write serious music that persists over time, you need a way to do that, and you need a way to do it in a very customized way that doesn't borrow or rip off from the sound files that have already been stolen by these services like Suno and Udio. And you need a way that you can go deep into the music to customize it and tweak it as you wish. If you have the words, then you can use your language. You can use that to drive the code, even if you're not good at coding. But if you want to, you can, as you can see here, drop down into the code and modify and tweak the piece in very articulate ways. And if you're not certain what to do, you can ask the AI how to do it, and it'll tell you in no uncertain terms how to alter the code to change the effect that you're trying to achieve. So this is a very powerful workflow. Like I said, it's automatable. It may look cumbersome now, but this is the worst and least efficient it will ever be. And I promise you that once I dial this in, which I believe it's already dialed in, but now that it's dialed in, I can repeat this, and each time I repeat the process, it's going to get more efficient and more effective. And I'll be able to generate music at scale and in a way that can actually, carve out a space for me in that marketplace of all the trash that's being thrown against the wall by the musical aggregators. So that's this video. In the next video, I'm going to share with you the actual compiled piece, Decline. It's up to you to decide whether it has any artistic merit or not. It's quite different, and I think you'll enjoy it. If you don't, at least perhaps this explication here provides a little bit of insight into the power of AI and how you can use it in a novel way to create your own music. This is a picture of John Chowning and some of his colleagues at URCAM. I believe that's Rizet or Rizet there on the left. I don't know how to pronounce his name. Sorry for butchering the French, but if you've ever used a Rizet filter or Rizet filter, that's the guy. And here's the computer that Chowning used for creating Stria. I'm going to end this video with an interview featuring John Chowning at CCRMA, aka Karma, at Stanford.
FM was not an invention, it was a discovery. It's from nature. It was all there.
Like you had it in your imagination. It ended up as the sound palette for a whole new generation that did a completely different thing with it.
I never thought that FM would be part of every dubstep, and I thought, never imagined. And the discovery was in your discovery. That's really important. It wasn't like I was a math major or somebody who knew about technology. I didn't. It was absolutely your discovery.